So we should be seeing Blackboard over there in Renfro. Is that right? You guys see Blackboard on the screen? Okay. Okay, dokie, here we go. So I've got up in course materials on Blackboard, I've got there's a really cool TED Talk about, she's a fun physicist, she's out of England, so her accent's pretty cool, and she's talking about physics in everyday life and where physics fits into things, and how she tried to explain quantum mechanics to her grandmother. So it's really entertaining when you try to take some of these concepts and try to explain it to the average person on the street. And they say, well, what are you studying in physics too? And you go, yeah. And how is this practical? Yeah. Well, we talked about simple harmonic motion being practical, and so so in week 1, you probably got pinged like crazy today, right? This morning, if you got things in there. Here's the place to put your example of simple harmonic motion. So things I don't want as an example, my good old clock pendulum, because that's one of the ones that we talked about, the good old clock pendulum. And then I'd like for you to come up with the wave equation for it. We've talked about the wave equation. I will show you another wave equation today. We're going to go over. I've got a PowerPoint that will put some pictures together, and hopefully it will sink in a little bit about simple harmonic motion in there. Then under resource items, I've got the links to the simulations. There's the one for the pendulum. Here's the one for Hooke's law. This goes in and looks a little bit about Hooke's law, and then there's a simulation of simple harmonic motion as well. So I've got those resources put in to help you out. And then I've got lovely little GIFs, and we've been talking about simple harmonic motion. So this looks at the bead going up and down, and you can see where it is on the curve at any time if I'm doing a y-axis. So that's one of the little GIFs that's there. This is looking at it from a spring point of view and looking where we are with respect to the spring. As time goes on, that spring is bouncing up and down, and you can see that little bit of where I am on the sinusoidal curve. Then this one, if I go there, this one, we talked about this on Wednesday, where I'm essentially doing the same thing as if I'm going around a circle. And so my drawing it on the board make a little different than actually seeing it next to the object. So there's that one out there that you can see it in a couple of different ways. And then I have one more, and this is a PDF on simple harmonic motion from the University of Colorado that may help a little bit. Now, granted, this is from a calculus version, but it's there for you just as an extra resource. So that should help. And then I've got, and remember, I can't post all my PowerPoints, and you'll see why today, because I don't have all the alt text in there. So, but you get it on the video. And I did get Wednesday's video posted already. So it's already out there for you guys. So we're going to start from this today. And we're going to cover a couple of, ask me later, a couple of the concepts that we did on Wednesday. And then we're going to take off a little bit more into wave motion. So where we were on Wednesday is we started with Hooke's law. You remember, we went back to Hooke's law, and we've got that kind of straight. And we started talking about the sine wave and how we had that image of the sine wave. And basically, and this may be a question that you're going to get on a quiz or a test, to be able to label the different components on the wave. So not only did we talk about that it was a sine wave and that the sine wave and the cosine wave look identical, it's just all a matter of where you start, there are other components to the wave that we need to worry about. We talked about amplitude. The amplitude goes from that center point to the top of the peak. It is not from here to here. It's not there. And that is the most common mistake that happens. People commonly will say, oh, it's that whole gap. It's not that whole gap. And I think that comes from when we start thinking about a mechanical wave on a boat. We feel like we're going all the way into the valley, and then we come all the way back at the top of the crest, and so we think that's the height of the wave, and that's not. That's not the amplitude of the wave. Okay, that's not the amplitude of the wave. So this is my amplitude. My wavelength is from any same point for one complete cycle. So I could go from here to there, and that would be a wavelength. From peak to peak would be a wavelength. From trough to trough would be a wavelength. And that's when I am dealing with length, okay? Because I can use that same picture to describe period with respect to time. So when you're drawing it on a test or you're picking things on a test, because I'm going to use the same methodology that I did before, just trying to keep up with things, I'm going to use multiple choice with the opportunity to have extra bonus points on there. But so you'll be picking which one. Be careful of what the axis is. Is this time or is this length? So am I doing length or time? If I'm doing length, this is my wavelength. If I'm doing time, that's my period. It's the time that it takes one complete cycle. One rotation around the wheel. And the pendulum, top of the swing, all the way over, and it comes back to the top of the swing. So we've got all of those different pieces. So this is our terminology that we have. And remember, frequency is related to 1 over the period. And frequency, this is what got people when we were doing rotational motion. That's what really got people kind of discombobulated, is that the frequency is the number of cycles per unit time. And our unit for frequency is hertz. Our unit for frequency is hertz. So we've got this terminology that we're familiar with it. We've used this all along. But one thing we didn't cover on Wednesday is the energy equations associated with Hooke's law. Because not only are we moving up and down with respect to motion, and then we derived and we showed the velocity of our object if it's bouncing up and down or going around a circle. And we talked about the acceleration if it's bouncing up and down if we go around the circle. We also have a change in energy, especially if I'm thinking about my spring hanging down. I know it has potential energy, and I know it has kinetic energy while it's moving, because kinetic energy is that energy of motion, and potential energy is that energy of position. And we've got our spring energy. So remember back from physics 1, right? We've got kinetic energy is 1/2 mv squared. My potential energy is mgh. And my potential spring energy is 1/2 the spring constant times that x squared. So we have our energy equations. And so also remember, going back, that we have conservation of energy. So historically, I used our lovely slide. And we talk about work getting to the top of the slide. At the top of the slide, it was all potential energy. Well, now with my spring system, not only do I have potential energy associated with the height, I have potential energy associated with either the compression or the extension of that spring. So if I'm at the top, I've pushed my spring up, and I'm getting ready to let it go, so I've compressed the spring. I've got, not only have I changed the position, particularly if I'm in the vertical, I've also got that spring potential energy. And then we know throughout the middle of our slide, we have potential and kinetic energy, and then at the bottom, it was all total kinetic energy. In my spring system, it's a little different, because at the top, of my amplitude, if I'm thinking about my spring being up and down in the y direction, I've got a compression, and at the top it's all potential energy, but when I cross that spot where my amplitude is 0, I'm all kinetic energy, and then of course I'm extending or lengthening that spring as I go down to the bottom, and I'm developing potential energy again. So my kinetic energy is going to be max when I'm crossing that spot where the amplitude is 0. Got a question? Are you okay? Okay, cool. Cool. So there's what it looks like when I've got my spring. So this is exactly what I was talking about. Here is where it's all kinetic energy. This spot, my total energy is going to be equal to the kinetic energy plus the potential energy due to gravity plus the spring potential energy. Down here, I'm at maximum potential energy. Then up here, I'm at maximum potential energy. And so I can go through this same set of curves in terms of energy and motion. So these things that you may want to remember that are out there, and we talked about these on Wednesday, that definition that we had in there and using the contention. So now we went back and we talked about velocity, and I showed you that velocity equation. Okay, that velocity equation, if we start out with y is equal to a cosine omega t, that was our position. Then my velocity was equal to minus omega a sine omega t, and my acceleration was equal to minus omega squared times my amplitude cosine omega t. Well, we can come back and look at and rearrange it so that we know our maximum velocity. So what is that maximum velocity when it crosses that 0 point? That maximum velocity when it crosses that 0 point. And that goes back to using our kinetic energy and our energy equation. And when I do that, the speed is maximum at x is equal to 0. That's as fast as it's going to go. So if I'm thinking about my pendulum, the speed is fastest down at the bottom of the pendulum swing. Because at the top of the pendulum swing, the speed is equal to 0 because it's changing direction. And we talked about that when we were doing our ballistic pendulum problems. So we use that pendulum to help us with conservation of energy. So we're bringing that back. And my speed is 0 at the top or the bottom of my piece. So we've got this right here as my maximum speed as I go through, and it's related back to my spring constant divided by the mass. There's my amplitude, and that's when x is equal to 0. That's my maximum, and this is the speed at any position throughout the motion. So you can use your conservation of energy to help us with the speed. These are the things we talked about on Wednesday. All right? These are the things that we talked about on Wednesday. That my sine and cosine functions are the same except for where I start. And I'm off by a phase angle. I'm off by a phase angle. Now, for simple harmonic motion, this is just whether or not I use the sine or the cosine wave. So in my lab, I'm going to use the sine. In our book, we use the cosine. But when we get later on in the semester, which is why I start with simple harmonic motion in Physics 2, some places you'll get in Physics 1, you'll get all this stuff. Because we're using a lot of Physics 1, right? We're using conservation of energy. We're using Hooke's law. We're using that piece. So I'm using those concepts, but now I'm putting it into the sine waves. So the question is, why put it here versus put it with mechanics? Well, one is if I don't put it here, when we get to sound, things get a little funky. And if I don't put it here, this phase angle that you see right there is not going to make sense when we get to alternating current. So when we get to alternating current, we're going to be on this same sine wave. We're going to see the sine wave again. We're going to see the root mean square information. And we're going to talk about how magnetism and electricity are related, and we end up with different components in our circuits. We end up with capacitors, inductors, and resistors, and this phase angle becomes very important when I'm dealing with capacitors, inductors, and resistors. So we see it again. So if I left it in Physics 1, it's been a long time since you've seen it by the time we get there in terms of circuits. So that lovely phase angle becomes important, and so it's really nice to pull it all together. So in your lab, for those over in Tonkawa, they've already done it. In the lab, you're going to do your position in terms of y. We're going to be in vertical motion rather than in horizontal motion. And you're going to come up with an equation for your line, or for the graph that you see. And so let's kind of look at that. This is our general form. This is our general form. And back on Wednesday, we talked about, okay, we know what the amplitude is. So if I go to my graph, my amplitude is going to be from here to here. And looking on this graph, my amplitude is going to be 7.5. We can also, since this is related to time, I can go in and read the period off here, and the frequency is 1 over the period, so I can plug in that value for this right here. So I can use this graph to plug in the values directly. So there's my amplitude, and we said it was 7.5. So now I can plug in that number directly into my equation. Then I can look at my period, and I can read my period off the graph in several different places. And when I do that, it looks like the period is about 2.1 seconds. My frequency is 1 over the period. So now I can put that into my equation, and so I can put in for F 0.48. So I put in my 7.5 for my amplitude. I can now put in the 0.48. And now I can put in there, and my phase angle is where do I start? And in this case, I start at 0, so that makes that nice and easy. And I can go and put that in for right there. So we can use those sine functions. Let's see, where am I going? Looks like I've got repeated. So that's my simplified equation. So I can go both ways. I can take the data on the graph and create my wave equation. I can pull information from my wave equation to what's physically happening. And that's kind of what we did on Wednesday. We talked about that lovely going around the circle. I can still use the same thing, but this time what we're looking at is what's happening on our x-axis or our y-axis, depending on where we are, which way am I going to do, that this becomes a projection on these axes, and it follows the same behavior. Talked about this on Wednesday. Looked at our angular frequency related to our spring constant and the mass. And we talked about and we kind of did these problems on Wednesday where I can look at it and rearrange it in terms of period, or I can rearrange it in terms of frequency. And I can get information with regard to that circular motion. So this is the same stuff that we did on Wednesday to get these particular pieces. So Wednesday kind of left it got to this point, and I think that's about where we stopped, right? We stopped right about here. No, we did the pendulum, because I've got my pendulum slides coming up. We did the pendulum. So when I start with my equations of motion, in terms of my simple harmonic motion, I've got my amplitude times the cosine and my angular frequency times time. And all of these currently are a function of time. When we get a little further, we're also going to look in this function in terms of time and position. And then we call something a wave function. So when we go over and you talk about quantum mechanics, for those of you who may be headed on more towards chemistry down the road, and they talk about, well, we're going to do quantum mechanics, and we're going to look at that piece. That's those wave functions that come in and make those pieces work. And those are the wave functions because we can move things. So I've showed you where some of these are in Blackboard. These are the links to the different animations that I've got, and you've got them in Blackboard. So you've got them in Blackboard. So we kind of ended there. Actually, for us in here, I'm going to come back here. Obviously, I've got it. We ended with this on Wednesday. We looked at the pendulum. And I kind of drew it on a piece of paper. We got back to the fact that if I looked at this, here's my angle that we had. We looked at it as we came into a swing. We talked about the circumference of the circle being related to the length of my pendulum. And we talked about for small angles, I could make that equate to pretty much a triangle. And that little bit of arc on my circle is pretty close to a straight line. And I can go back to my angle and relate my angle back to the geometry of my pendulum. And we went through this derivation on Wednesday. They said, all right, my force is minus mg times the sine of the angle. And we equated it back to the S and L, the S being that little bit of distance through here, L being the length of the pendulum. And then, then we went through this part of it and said, okay, let's go back and look at frequency, and let's go back and look at that piece. And we got, in terms of period, in terms of gravity. And I don't have to worry about my angle anymore. And I don't have to worry about my arc anymore, which is really, really nice. And then we could come up with an equation for period related to the length of my pendulum and gravity. And we could determine an average period, and we could do a pendulum, and we could calculate gravity depending upon the arc length. So you can try this at home with a string and a nut. Any kind of plumb bob works. You can actually measure gravity. Turns out in Physics 1 and Physics 2, I don't know how many times did you guys measure gravity in the lab last year? At least twice that I can recall. My engineering physics people end up measuring gravity at least 3, 4, 5 times. So we measure gravity a lot. It's easy to do. So here's a question for you. When we drop an object to the earth, does the earth come up to meet the object? When we drop the ball to the earth, does the earth come up to meet the object? How many people say yes? Raise your hand. Okay, guys. How many people say yes? How many people say no? I want to make sure you're all awake. The answer is yes. You knew it was going to be a trick question, right? Okay, and I'll show you why. So remember Newton's law of gravitation. F is equal to this big G M1 M2 R squared. Okay, I'm going to go out just a little bit. We've got a bad glare in this room. 110 is always a fun room to fight. Okay, can you guys see the equation over there in Tonkawa? Okay, all right. So that's Newton's law of gravitation, right? So basically what that says, and we normally think of it this way, here's my earth and here's my little ball that's fallen to the earth. We normally think the ball is falling to the earth, but remember back when we took two objects, and if the objects were very close in mass, we knew that this object was being attracted to there, and we know that this object's being attracted to there. We know that even on the earth, because of my moon over here, if I got the moon, why do we have a tide? The moon is pulling the water towards it. The moon stays in orbit because the earth is pulling the moon towards it. So we actually have the two forces going back and forth. The issue is here, and why we don't perceive that the earth is moving up to meet the ball, is that this number right here, this mass is so big in comparison to this mass, the little ball is not moving the earth a whole lot. So we have an imperceptible force that's coming back to have the earth move back up. And this is something that in like week after next, we need to kind of know, because when we get to electrostatic forces, we're going to see this mutual attraction become real important. It's not so important when I have a little mass like my ball related to the surface of the earth, because my little ball is not going to make the earth move perceptibly all that much. My masses start changing, it will. So we do have that piece, and again, that's going to become really important as we start getting into electrostatic forces. So the earth does move to meet the ball that's falling down. And so don't worry about whether or not you said yes or no. Okay? Because in practicality, it doesn't. Right? In practicality, we don't see any perceptible motion of the earth coming up. And that has a lot to do with our scale and where we are. But when I start dealing on an atomic scale, it's huge. This is an important thing. If I'm dealing with galaxies and I'm dealing with planets, it's huge. It's an important thing. It's where we are and related to scale. So our pendulum back there, we can measure gravity, and we know exactly, we know exactly what it was. We also talked about dampening, because this is easy to see with our spring system in real life. We normally disregard air resistance, but when I've got a spring bouncing up and down, I get air resistance. Not only do I get air resistance, I get resistance associated with friction in my spring. If I let it go on long enough, what happens to my spring? Oh, come on. It's how I microwave, right? If my spring is vibrating a lot, what happens? If I don't have vibrations in my spring, is my coffee going to get hot in my microwave? So the vibrations cause what? Friction. And if I'm going to get that friction, my spring is going to heat up, which is why my coffee gets hot. Except my coffee doesn't get hot because I don't drink the stuff. But that's why we worry about friction. Now we also know, and this because friction drives us all crazy, because friction is our friend and friction is our biggest enemy. That's why the second law of thermodynamics is a pain in the tush. That's because we're going to lose it due to friction more than anything else. But if I'm on and bouncing up and down on my truck, and I'm getting it to bounce up and down in my truck, and I've got the old classic shock absorbers, and I've got the old classic spring, and if my shock absorber is starting to go, what's going to happen to that lovely shock cylinder? It's going to leak, and eventually I'm going to bottom out and I'm going to break something. And we also know that if I fold paper back and forth or fold a piece of metal back and forth, back and forth, back and forth, it stresses it out and it ultimately breaks. So we worry about those vibrations because that's why something's going to break. Not only do we have to worry about resonance, and we'll talk about resonance when we get to the next chapter and we start talking about sound, but we get things that break. So dampening is a result of friction, and we can use that for different pieces. All right. So we've been talking about simple harmonic motion. Kind of covered everything that we covered on Wednesday, kind of gave you some nice pictures, some nice equations. Hopefully that's going to help us go forward. But we do this to just start describing wave motion. So depending upon where we are in the book, I'm either at the very end of one chapter and we're starting to creep into the sound chapter. We're starting to creep into the sound chapter, which reminds me of the following. Next Friday, we will not have class. You have a quiz. The quiz will be released. I think the quiz was released next Wednesday. You will have a quiz. The quiz is due at 5 o'clock on Friday. So you've got some time to work on the quiz. The quiz is over mostly simple harmonic motion, some of this wave motion. So you've already got that. I will be on my way to an American Chemical Society leadership meeting, which is why we're going to be doing it that way. So you'll have your homework to work on. So we will actually physically not meet class next Friday. And to the best of my knowledge, that's where we're going to be until after spring break. My other meeting usually falls on spring break, but this year it doesn't. It's going to fall after spring break. So we'll keep you posted on that. And odds are that'll be about the time to do your take-home circuit test. So it usually works out really well. So next Friday we won't meet. I'll post on Blackboard, and you do have a quiz to take care of that. All right. So we are going to be talking about mechanical waves. We're starting with mechanical waves. Now, we have other kinds of waves, all right? Electricity and magnetism, we get there, and we ultimately get to electromagnetic waves. But right now, we're starting with mechanical waves. And we're all familiar with mechanical waves. We've seen the water, when we drop the pebble in the water and the wave starts floating off, right? We know that kind of a wave. A mechanical wave, and any wave, whether it's electromagnetic or mechanical, it is a motion of a disturbance. We get some sort of disturbance associated with it. But mechanical waves are going to require a medium. They have to have something in order to be moving through. So a mechanical wave has to have a medium. So that medium could be a string, because we can think of a mechanical wave in a string. I can send a pulse in a string. I can send a pulse in a spring, and on Wednesday I'll bring a slinky because it's very difficult for me to actually talk about waves without having a slinky. But I can get some sort of disturbance. And most of us have seen the classic, what we call the bell jar experiment. They take an old classic alarm clock that's got a peal at the bell between the, and you see it hitting the bells, and as they create the vacuum in the bell jar, you can still see the motion of the hammer going back and forth between the bells, but you no longer hear the bells. Because the vacuum has pulled it out, there's no medium for that sound to actually move through. Therefore, you can't hear it, because sound is a mechanical wave. So we rely on a medium in order for it to happen. So I'm going to have a disturbance. So mechanical waves require a medium, and they require some source of disturbance. We have to have a pulse. We have to have a pulse of some sort. So I guess we had an earthquake earlier this week. It was in Kima. It was like 3.2. And most of us have been experiencing these earthquakes. A couple things that we know about the earthquakes that we get. Sometimes the earthquake is just a jolt, right? It's just something like that. But, oh, this room actually was pretty good because it actually heard a vibration that went on, right? We heard a vibration that went on. So you had a jolt. And sometimes we've had an earthquake where you feel that roll, it lasts for a long time. The intensity may have increased and then it decreased off, but we had that last for a long time. Some of them you hear, right? We hear them. In fact, when I lived in Utah, I actually lived with my basement into one of the mountains, and I could tell certain places because the mountain range was right along that range that if you looked at the top, Yellowstone was, and every now and then we would get a sound in our basement that the first time I went to check on my kiddos thinking that they were crying in the middle of the night or moaning in the middle of the night. And it turns out it was a resonance frequency in my basement, and I could see and track it with an earthquake. We could actually hear them. We never felt them, but we could hear them because of the resonance in my basement. So we can hear them. So we have to have some sort of disturbance. So if you think about that disturbance with an earthquake, usually what's happening is I'm breaking something or something has fallen, and because of that fall, it's going to create that disturbance, which is going to generate a mechanical wave. So we're going to get mechanical waves. So mechanical waves have to have a source of disturbance, and it has to have a medium that can be disturbed. So it can be air, it can be water, it can be a table, it can be steel, it can be a variety of things. But whether or not I have a mechanical wave or an electromagnetic wave, all waves are going to carry energy and momentum. And we can see blast waves, right? So we have a big, huge explosion, and you can see that blast wave. And you can see what happens. It knocks things down. We know that energy is out there. We can feel them. I mean, we know we can feel them. So, okay, for all of you medical types, and this is one of the ones that puzzles me greatly. If you're going to the sonography program, it doesn't matter which school you go to, you get sound and physics too. And you're going into the sonography program, you don't have to take physics too. I'm puzzled. Because what's sonography? It's how sound waves, it's creating images using sound waves. So I'm really puzzled. Because this is the basis for sonography. Is we're going to create sound waves we create those sound waves in order to get images. So, we have two types of waves. These are mechanical waves. Okay? These are mechanical waves. We have two types of them. And we're familiar with them. This is why I can't do a wave demonstration without a slinky. Okay, we can't do a wave demonstration without a slinky because we have two types of waves. So think about a string. So if I have a string here, I can send a pulse. That's my wave that's going through my string. So I get that nice pulse and it goes through and it's going to travel. And if I think of what's happening to this little section of the string, it's going up and it's coming back down. It's going up and it's coming back down. And it's going to look like a little sine wave at that spot. Think about your bobber. If you're fishing and you're using the old classic bobber method, you've got your weight down there and you've got your bobber up there and a wave comes by. What happens to your bobber? It floats up and it floats down and it comes back up and it goes down because I've got a disturbance associated with it. This is what we call a transverse wave. You can think of it as it's going up and down. I've got a nice disturbance that goes up and down, and that's a transverse wave. You're likely to have on a quiz or a test, just tell me the difference between a transverse and a longitudinal wave. Longitudinal waves, that's why you got to kind of have a slinky, because it's easier to picture on the slinky. Because what happens is I can put the pulse through the slinky and it's going to compress the spring, it's going to stretch the spring, it's going to compress the spring, and it's going to stretch the spring. And that's a longitudinal wave. Turns out earthquakes can have both transverse and longitudinal waves. So you may have seen, depending on where you are, or way back when in your earth science class back in elementary school or middle school or early high school, they talk about S&P waves. They talk about primary and secondary waves. Well, one typically is a transverse wave and one typically is a longitudinal wave. The transverse waves, if you've ever seen the pictures of the Alaska earthquake, just a second, the Alaska earthquake in 1964, they had cameras in certain places that you could actually see the rolling of the surface of the earth, and almost fluidized, and it would roll and you could see it, and that's a transverse wave. Conversely, the longitudinal wave is a compression and an extension, and you don't see it quite as much as you would see that, what we would call a rolling wave, more of a transverse wave. So we get those different kinds of waves. So longitudinal waves can still be represented as a sine curve or a cosine curve, except now I'm dealing with a density aspect. You know, my density increases and it extends, and it increases and it extends, and it increases and it extends. And when we do that increase and extension, we can relate it back to pressure, okay? Since it's carrying energy and momentum, we can relate it back to pressure. If I'm increasing the density, I may be increasing the pressure, I can go on. So now let's think of a sound wave. Let's think of a wave that's being generated by a speaker. The speaker, if you've ever watched your speakers, right, you know that the speaker is vibrating forward and backward, forward and backward, forward and backward. So if you think about the speaker being a plunger, as it moves forward, it's compressing the air. As it's moving backward, it's creating an extension of the air. So it's essentially sending a pulse of compressed air. You can think of it that way because the density is increased right there, and it's pushing it through the medium that we have, and that medium happens to be sound. So if you think about sound and what's happening with sound, as your vocal cords compress it, it's sending out a pulse of a certain frequency. I've got that packet of dense air molecules. They extend as they move forward because they're having collisions with the next set, right? So the collision pushes it forward. So that old Newton's cradle thing is happening. One ball hits the next ball hits the next ball, it goes down, and it's pushing that energy down the way. And after that collision, it's rebounding a little bit, so I'm going to get that extension until it ends up hitting a receiver. So I'm going to get that compression, I'm going to get that density, and I'm going to have it move back, and it's going to be from pressure waves. I still am going to have amplitude and wavelength. If I can represent it as a sine wave, I still have amplitude. And in the case of that density, that amplitude is going to relate to how dense is it. Okay? It's going to relate to how dense is it. It's going to relate to that increase in pressure. It's going to be more of a physical part of it for that amplitude. Now, on a transverse wave, the amplitude's easy to see. How tall is the pulse? Right? So if I'm in there using those lovely weight training ropes in the gym, how big can I get that pulse? That's going to be related to my amplitude. If I'm dealing with a longitudinal wave, it's how dense am I going to get that material in comparison. So transverse waves, pretty easy. Whether it's a wave in the water, whether it's a wave in a string, along those lines, how tall is my wave? My wavelength is how, from one end of the same point, one complete cycle. So we know if I'm traveling on the pond, right, and I throw in a rock, we can see that wavelength. We can see how fast it's moving as it moves out. If If I've got a boat that's going slowly, we know how those waves and crests are going to come and affect my fishing bobber. If it's going faster, we know how fast that wave is coming to affect my fishing bobber. So my wavelength is between the successive points, no different than when I had my sine waves that we were seeing in simple harmonic motion. So now you can start to see why I go there. Because I wanted you to see where the physical part of the mathematics come from before we get to where we're headed. So transverse waves are easy to see. Longitudinals will take a little more time to see, but I could still represent it as that nice sine wave. And I can still take that information right off of there. The amplitude is how high is my wave. My frequency is in there, how fast that's traveling from point A to point B. But now I'm going to make it just a slightly bit more complicated. In simple harmonic motion, I only worried about time. So let's go back and look at this. I only worried about time. But now my pulse, this pulse, not only is moving with respect to time, this pulse is now moving with respect to distance. It's moving from this end over here to this end over there. Not only do I have to worry about how this is going up and down, I have to worry about how this pulse is moving through the medium. How that pulse is moving down that string. So now I have to worry about where is it? Where is the pulse? So wavelength is still there, amplitude is still there, but now I have to worry about where this thing is moving. Now most of you have all had chemistry and you've seen this lovely equation before. That the velocity of the wave is equal to the frequency times the wavelength. Think about your units. Frequency is in 1/seconds. Wavelength is going to be in meters. And so if I have meters times 1/seconds, I get meters per second. So I've got a velocity. So I can use my unit analysis to help me work through this. It's derived from our basic, way back when we did our kinematics. I've got my distance over time. But now I can actually start seeing that velocity of the wave that we're working with. You're going to see this again in electromagnetic waves, but we know something about electromagnetic waves. They all travel at the speed of light. Mechanical waves don't do that. Mechanical waves are impacted by their medium, so my speed is a little different, but I'm still going to use the same equation. Speed is equal to the frequency times the wavelength. And we know that it's a general equation. We can use it for any kind of wave. The difference is when we get to electromagnetic waves, we know what that speed is. So, if I think of a guitar, okay, on my guitar, and I'm going to go ahead and use a 6-string guitar because that's the one that most of us are familiar with. On my guitar, I have 6 strings. If I go to the guitar store and I buy a string, he's going to want to know which string is it. Because when I look at my guitar strings, we know typically most of us only see 2 different types. We see the ones that look like fishing line, right? They're the thin ones. And then we see the ones that are a little thicker, that look like it's a string with a coil around it. And they're thicker. So they don't have the same density. And usually refer to that as linear density, where it's mass per unit length. They don't have that same density because the tone that I want to get is not going to have the same tone. And it's because the velocity through which that wave, because basically what we want to do on a guitar is set up a standing wave. And we want to set up a standing wave to get a resonance so that we can get a pleasing sound. That's what we want to do. So there's a couple things that I can do. So if I think of the inside of a piano, I can adjust the overall length of my string. I can change the thickness of my string, and I can change the tension of my string. Okay, those are the things that I can change. So on a guitar, we deal with the thickness and the tension. Where I place my fingerings is how I'm going to change my length. Okay, when I'm doing it on my fingerings is where I'm going to change my length. But what I'm essentially doing is I am creating a mechanism by which I'm changing the velocity of the wave that's happening inside that string. And ultimately what we're trying to do is create standing waves to get resonance. So the velocity of the wave, so if I have a string, how tight I pull the string is going to impact the overall speed with which the wave is going to be able to travel. And that's where this comes in. So the speed on a stretched string actually works out to be the square root of the force, or the tension in the string, divided by the linear density, or how big or thick is my string. And if you think about it, if you think about trying to create tension in one of those exercise ropes, it's hard, right? You got to kind of lean into it. And how fast you can create that pulse through there has a lot to do with how tight you can keep the rope, right? So, and we know what kind of force it requires on those ropes because of how massive they are. So you will have some homework problems related to the speed at which the wave is going based on the linear density of the string. But what I want you to get out of this is, so let's take our sonography example. Okay, let's take our sonography example. One of the reasons we can get an image is because what's my density of bone compared to the density of fat compared to the density of muscle? So if I'm sending a wave through those three different materials and looking for the reflection of those waves coming back, they're going to come back at different rates depending on the different type of material, because the density is going to be different. So the frequency with which I'm putting in the sound is going to be the same, but it's going to take it a little longer to travel through fat because it's not as dense. It's going to go a little faster through muscle, and it's going to go a lot faster through bone, because the more dense it's going to turn out, the faster it's going to move. So if I use that sonography example, we know that the density is going to make an impact. We also can use this, that's where they go out with the thumper trucks in terms of in the oil field. Because rock is going to have a different density than oil, which is going to have a different density than gas, which is going to have a different density than sand. And we can draw a picture based on how those sound waves come to the detector. It's how your fish finder works if you're into fishing. The density of the fish are a little different than the density of the water. So we know that density is going to impact it. And so we look at it in terms of wave on a string, but it really comes back to how are we going to use that information. So you have a couple homework problems on that. So here comes why that's one reason why it's important. Okay? But we also are trying to talk about standing waves and interference, and I've been talking about those things, and we want to know what's going to happen. And interference of waves interference of waves are things that we deal with. So let's think of a kiddo on a swing. We're pushing a kiddo on a swing, and the little kiddo wants to go higher. Well, if the little kiddo wants to go higher, we have to time our push just so that I don't have to put a whole lot of effort in, I can send the kiddo higher with a bigger push, or I can send the kiddo higher with a little extra push each time the kiddo comes at a certain spot, and I don't have to put as much force into it, and the kiddo's still going to go higher. Because what I am doing is I'm creating an interference that's additive. All right? I'm creating an interference that's additive. That's what's going to happen when I do the resonances in an organ pipe, or I'm doing a standing wave resonance, or I'm doing a variety of different things. I'm creating that I can add weight. Waves are going to add to each other. Waves are additive. So when I put in a pulse and I put in a second pulse, I'm going to see those pulses go together, and the wave that the two pulses are going to add or subtract, but they're going to be independent of each other. And that's what we call interference. So they're going to interfere with each other. Sometimes they're going to positively interfere with each other, and sometimes they're going to do what we call destructive interference, and they're going to cancel each other out. And that's why your noise-canceling headphones really work, because we're adding frequencies and stuff in order to purposely get that interference to cancel each other out. So we use something called the superposition principle. And what that does is says two or more waves traveling, they're going to encounter each other, they're going to add together, and they will work to go there. Typically, this is true with only small amplitudes, but small amplitudes are relative. This model works for a lot of different things. But if you think about it, I know you all did it. Everybody's done it because everybody's gotten in trouble for it. At one point or time in the bathtub, you sat in the bathtub and you created a wave. And it was fun to get the wave bigger and bigger and bigger until the water splashed out of the bathtub. We've all done it, okay? May have been a long time ago, but we've all done it. But that's what whitewater or whatever it is, or the different splash pads or whatever, when they're creating the waves in their big wave pools, they're doing the same thing. The idea is to positively affect it so that you're increasing the amplitude so that you can add the superposition in there and you're creating a great big huge wave. And that's what you wanted to do. And we use it. And so it is relative. We look at these superpositions. So we've seen it. You see it on the ripple pond where we have constructive and destructive interference. We see it with light. We see it with sound. That's how we do, you make soundproof rooms. We set it up so that you're creating to get destructive interference. And we set it up with pipes and resonance and strings to get constructive interference. It's also why if you're marching across a bridge, nobody's supposed to be marching in step, because you don't want to set up constructive interference and ultimately break the bridge. It's what happened with the Tacoma Narrows Bridge. Constructive interference got bigger and bigger, and that wave got bigger and bigger and ultimately disintegrated the bridge. So constructive interference, we're going to add it together so that we increase the amplitudes. Destructive interference is such that we're going to cancel each other out. And it's all based on the superposition principle. So we can look at our constructive interference. If they're the same size and we get constructive interference, we end up with twice the amplitude. If they're the same size and we get destructive interference, they cancel each other out. And we've seen it and we've played with it. But the key here is if I'm adding my wave equations, these are exactly 180 degrees out of phase. That phase angle comes into play. That phase angle comes into play. So here are two waves that are going to constructively and destructively interfere with each other. So I have a pulse that's going this way. I have a pulse that's going that way. as they merge together, this pulse is still moving that way, and the bigger pulse is still moving that way. When they're on top of each other, they've got total constructive interference, and we get the aspect there. And then they will pass through each other, and this pulse is still going that way, and this pulse is still going that way. And I can actually see the motion of the wave. And you can play with it, and a lot of us have. If you ever played jump rope, I know you've played with the different pulses, you've sent pulses back and forth, and you've watched it. It's something we've all played with. We just don't remember playing with it. But we use it to our advantage in noise-canceling headphones. We use it to our advantage in concert halls. We use it to our advantage in a variety of different things. We also know that in a concert hall, there's usually a place that's got what we call a dead spot. The architecture and the construction is such that we have it to where it goes in, and no matter what you do, you got a dead spot. We also use it where we know we've got traveling, that if you've ever been to the Science Museum and there's been some parabolic mirrors on in one corner and one in the other corner, and if you stand in just the right spot, you can whisper, and a person clear across the room can hear your whisper. Turns out the United States Capitol in Washington, D.C. has one of those spots actually in one of the chambers. It wasn't intentional. It just was one of those spots where they discovered it, that the actual architecture of the room created it so where it sounded like somebody was throwing their voice. They're not. It's just the way that the room reflects it, and we get a spot where there's constructive interference, and you actually pick it up. It's going to focus that sound into that one spot. That's why if you walk into a room that's supposed to deaden the sounds, what do you see on the wall? You see the walls are really rough and irregular, right? The walls are incredibly rough and irregular. A lot of them have little styrofoam pieces, and it looks like little egg cartons, and it's because they're trying to set up so much destructive interference that the room is going to deaden any of those other sounds. So we actually use this to our advantage. So destructive interference works the same way. I can still have my pulse, and I'm actually going to see a wave that it's kind of canceling it's out, canceling each other out. So we get that destructive interference. So we can get reflection. Reflection, as it hits the wall, it will flip over as long as I have a fixed end. And this is something that we've seen before. If we bounce, that we get the shape. The shape of it remains the same, but we can get reflection. If I don't have a fixed end, it's not going to reflect the same way. And it's all about how the wave is moving that momentum and how it's coming back. So we get that. And that puts me through our wave motion. So let's go back here.